Okay, we definitely have to get back to Banduric about some of those specifics. We're going to be working on that experiment. Jeremiah knows a little bit more about it than I do.
So, Mark, if I could jump in real quick, you had talked about kind of a lab update. Would this be your lab update segment then?
Yeah, so everyone can see there's actually two Mark Sokols over here. The other one is on my cell phone. And I'm going to be, instead of moving the laptop around, I'm just going to be grabbing the cell phone and give you guys an update of what we're doing. We're trying a lot of different experiments. Of course, we're doing Alzofon, and that's dynamic nuclear orientation, which in a nutshell, for those who don't know, we're trying to create a state of coherent matter, which is my favorite way of explaining it is the second law of thermodynamics states that everything goes from a state of order to entropy. Like the egg falls and it cracks and it becomes a mess. Life, of course, is the opposite. We're able to create order out of chaos, but law of nature is everything goes toward chaos. And the same is true in the core of the atom. And all of the subatomic spins are all going in different directions, completely random. And there's several different spins to a spinning subatomic particle. You have the spin itself, and then you have the axis of the spin, and then the spin of the axis, which is called the precession. And I believe that that is actually the source of the inertial field, meaning that when you have these complex spins going on in the core of the atom, and you move the atom from point A to point B, you affect the precession or the different spins of the subatomic particles. And that is, it either energizes them or de-energizes them. And that's where you get, relative inertia from. So that would also, come into gravity, because whatever effect, wherever the gravitic field is coming from, it's not from the electrons, which make up only, 1/1800th of the weight of the core, or depending how many electrons there are. It's coming from the core, and if the core is random, then the field that is this gravity field is probably also random. So by orienting the subatomic particles in the core of the atom, we should be able to either create some sort of inertial dampening effect. It's not really going to make thrust. There is some theory about that as well. There's a couple different theories about why it will work, but in a nutshell, what you need to do to create dynamic nuclear orientation is something similar to what goes on in an MRI machine or an EPR machine. What you're doing is you're creating a homogeneous magnetic field, which is pretty difficult to create. There are machines that do that, like those big fat EPR machines where they use a ton of iron. We weren't able to get our hands on one of them, so we had to make one ourselves, and Jeremiah helped me out with that. It's a pretty small device, weighs around 100 pounds, basically just a big electromagnet, and we were sitting there agonizing over every difference in like 1 or 2 Gauss. We had to make sure that the entire field is homogeneous, or the entire area where the sample is going to sit is homogeneous. And then when you do that, it orients the electrons, because magnetism is, I think in its simplest form, you can call magnetism spin orientation. So electromagnetism is spin orientation of electrons. The stronger the magnetic field, the more spin orientation you're getting. Now, when you're orienting the core of the atom, I like to call that nuclear magnetism. And just like regular magnetism, the effect should be, it should transfer from the object that is coherent, that is polarized, to surrounding objects as well, and give them the same effect. And this would theoretically allow a craft to become almost weightless. If you achieve 100%, you should be able to go faster than the speed of light. And it would also allow a craft to do the 90-degree turns at 10,000 miles an hour that they've seen with the Tic Tac and with many flying saucers, or what I like to call them is interstellar extraterrestrial spacecraft, UFOs. I see them all the time. There's tons of birds and planes that I don't know what they are. So that's technically an unidentified flying object. So this is one theory that I really liked. I connected with it because it gave a coherent explanation to how these craft work and why they're shaped the way they are. Because if you think about the shape of a magnetic field, you have a big coil. Where would the laminar or the homogeneous field lines be? Well, of course, in the center of the coil, you'd have a homogeneous field lines. But if you can't build a craft like that, so you'd have to go outward, and it would sort of be a flying saucer shape if the effect was created from the shell of the craft. Then you would need to energize the electrons at their Larmor precession, because what the magnetic field is actually doing, it's not perfectly orienting the electrons, it's only orienting them to a certain degree. So you're creating coherency in the electron spins. That's what a magnetic field is. And that coherency is not perfect. They're still wobbling a bit. And you're able to measure that wobble based on its magnetic field, and it's about 28.025 gigahertz per Tesla. So at 1 Tesla, the precession of the axis, or the Larmor precession, as we call it, happens at 28.025 gigahertz per Tesla. Just for reference, the precession of the Earth happens once every 25,900 years. But an electron is spinning at the speed of light, and it's in this tiny little space, so it's spinning extremely quickly. We're not going to be able to interact with that directly. We're able to interact with its Larmor precession using gigahertz signals, which are way up in the microwave range. And then you pulse the microwave energy, because what you want to do is energize these electrons, like either spin them a little bit, and then then you stop the pulse, and that energy has to go somewhere. So via hyperfine coupling, which is the connection between the core and the outer electrons, the orientation is transferred into the core, and you slowly build up, step, you build up dynamic nuclear orientation. This also explains why flying saucers are seen to be, hovering. They're like, oh, they spotted us, we're on camera, we got to get out of here. But they can't just move right away because they're at 95% weight loss or 98% weight loss, whatever they're at, and they need to achieve those high 9s in order for their thrusting device, which is a separate component, to achieve lift. Now, if the craft is virtually weightless, one of the greatest ways to achieve a thrust would be light, because then you don't have to carry any propellant on board. Just turn on a light. That creates a tiny amount of thrust, but that's enough to get you to the speed of light if you're weightless. And that's how they fly off at crazy speeds. Why they don't interact with the air is still a mystery to me. But that is one experiment that we're trying. And I'm going to transfer over to my phone over here and try to give you guys an update from the lab. Can you hear me on the phone? Can you hear that? I'm not sure if
No.
Join audio. All using internet.
There we go. You're going to get feedback.
Okay. How's it now? Okay, so I have to. Okay, I have to mute the.
Yeah, there you go.
Okay, I have to mute the computer. Okay, perfect. So now I'm just going to walk around the lab a little bit, show you guys what's going on. The lab is a freaking mess because we got funded, but a lot of stuff is coming in the mail, and there's boxes everywhere, and we're doing this really on a shoestring budget. This is the dynamic nuclear orientation setup. So this is a signal generator. It goes from 9 to 9.5 gigahertz. That's X-band. This is on top of it is the traveling wave tube amplifier that's capable of putting out 20 watts. So that setup can work at 20 watts. So this is a new signal generator that we just got that I haven't tested yet. I want to try that out actually later tonight. That goes all the way from 5.4 to 12.5 gigahertz. So we'll be able to get a much larger range with that signal generator if it works properly. I also have to check the impulse settings on it, whether I can get the correct impulses for the sample. There's a specific impulse duration that you need, which is dependent on temperature, and it also depends on the metal the craft is made out of. And this is all based off of a paper from Frederick E. Alzofon, Antigravity with Present Technology. This is why we call it the Alzafon Experiment. And this was published in 1981, and it's a peer-reviewed paper. It goes over, his whole theory and his experiment, and the experiment is laid out here, I think on the 3rd or 4th page. Oh, here it is. Yeah, it's basically the same thing, but instead of having a pulsed microwave source like we have, they were using a steady microwave source, and they had a little modulating coil to take care of that. And that's the homogeneous magnetic field. Now, this was all inside of a waveguide, a tuned waveguide, which is something that we're struggling with. We need to figure out the shape of that. And I got this book on waveguides, but it is so full of math, I really can't make heads or tails of it. This is another great book on dynamic nuclear orientation by C.D. Jeffries. This is available online, but having hard copy is great. We got a whole bunch of other papers over here as well. So getting back to dynamic nuclear orientation. So what we're trying to do is get the laminar or magnetic field and tune that with the signal generator's output. I found that this signal generator is completely analog inside. There's a whole bunch of gear sets in order to move a pin that goes inside of a tube. So it works off of a tube, and the numbers on there are completely inaccurate. We're relying on the numbers that we're actually getting from a field probe coming off of this signal analyzer, spectrum analyzer. This one goes up to 22 gigahertz. It's the Hewlett-Packard one. Here's a couple of probes that we have. These are all for microwave range frequencies. I don't know if anyone here is familiar with these type of probes, but there's a lot of different ways to do these things. And these all, I believe, are just testing the electric component of the field. I also wanted to build one using, test the magnetic component of the field. That would just be a tiny little coil. Over here, we have our DC power supply. This is what is powering the electromagnet. And it's a cheap Chinese one. It's not super stable. We have a much more stable, old style power supply. It actually weighs like 150 pounds. It's coming on a pallet. We're going to have to take it off at the forklift. And that's going to be humongous and give us a much more steady power for the electromagnet. And the reason why it needs to be so steady is because you change the Gauss by 10 Gauss or something like that, and you're already way out of your frequency range. So this needs to be extremely steady. To measure that, we built this custom shunt over here, which goes to a fluke voltmeter, which isn't attached at the moment. And all of these wires and all these components are all going through these holes in the wall. And you'll see why in a second. Here's a simple scope. This is for measuring the pulse lengths. Now I'm going to take you to the other side. This is our Faraday cage. So it's a room-size Faraday cage. You can literally walk inside of it. We have the little alarm light on to warn everyone to stay away. There's nothing powered in there right now. This Faraday cage is a capacitive shielding one, and I actually had a question for Banduric. Do you think this would stop a scalar wave? Because there is 2 layers, and they are capacitively linked. There's capacitors every square foot. You can see there's little capacitors that are put in there. Would this stop a scalar wave?
No. Yeah, I think it would. One of the tricks that you want to do also is use layers too. So I think having 2 or 3 layers, like they're capacitively coupled, would probably work.
Oh yeah, think about this: the Arna Kodesh, or the what was it in the Ark of the Covenant, was a bilayer capacitor. Faraday cage. So I wonder what kind of radioactive material was in there. Here, I'm going to go. I'm going to go inside the Faraday cage right now. I might lose you guys for a second. I'll leave the door wide open, but here is our logo, Falcon Space. We call it Falcon because because that's my last name. Sokol means Falcon in Russian. So here's the connections are all coming in here. The wires for the electromagnet. We also added in a massive capacitor to give the power supply more steady load. And we like to give everything funny names. So we're calling this the EPR NMR laminar spintronic alignment rig. That's really just an electromagnet. On the other side over here, we have a tub of salt water, and that's to capture all the extra RF. The whole waveguide design is not in the cage right now. It's out on the test bed. Over here, this is a spy cam, and we're able to see the sample, from the control room. Oops, I just covered the camera. So that's the spy cam. Over here is the actual sample rig. Now the sample has a little bit of iron in it. It's like 2% iron. And the rest of it's high purity aluminum inside of an epoxy. So even though it's in a laminar magnetic field, it will tend to want to twist, to have a little bit of a torsion on it. So we designed this nifty little device using our 3D printer. And what it does is it stops it from twisting. Like if I twist it like that, you see it kind of goes back into place. And those strings kind of keep it and keep the the freedom of motion in just one direction, just up and down. And there's lead weights that I pounded out for tensioning. Over here, okay, so the setup for the scale. Next thing goes to this tension rod or multiplication rod, which goes to a brass rod, and then there's bearings over there, and then this whole chunk of metal is actually our force meter. Now, the reason why it's covered in a whole bunch of metal is because there is a piezoelectric transducer in there, and piezoelectrics work off of electricity to give you the weight measurement as you squeeze them. And as you hit certain frequencies in this chamber with microwaves bouncing all over the place, you're going to affect that scale. So it needs to be grounded very, very well. And that was one of the false positives that we were getting, and actually got some ribbon cable to replace this thin little wire and go directly down the ground. And we also added a bilayer of metal over here directly in between the sample and the scale. That also helped with the shielding. In terms of shielding for the lab itself, these are covered, and that's pretty much the inside of the Faraday cage. The floor is made out of, I think, 1/4-inch aluminum. The grounding rod in the center goes down 8 feet, and there's a separate grounding rod for the outer lid. It's in the corner over there. And on top of it, we have just a whole bunch of random equipment. Ozone generator. This is our melting furnace for making different samples. We also got a gas one that just came in. Another thing we wanted to try is different types of samples. So we compiled a list of a whole bunch of different materials that we thought would be kind of interesting. I'm just going to read these off. And most of them are in powdered form. And the reason why we're using powdered is because microwaves have a very thin surface penetration. So aluminum, iron, niobium, bismuth trioxide, vanadium, copper, nickel, silver, magnesium, and tin. And the reason why we're going with all these different samples is mainly because bismuth I thought was kind of cool because it's a strong diamagnetic material. Also, I'm kind of curious to see what would happen. What would happen with dynamic nuclear orientation or nuclear magnetism with a material that has a high spin ratio, because it already has a high, a high nuclear spin. What happens if you orient it? And these are different mixes of all those materials. These were created by mixing them together with epoxy. We then put them inside of a vacuum chamber to degas them, and created these little samples with numbers so we know which one's which. I also have some ultra pure aluminum. Now, the reason why he recommended aluminum, and especially ultra pure, is because aluminum has a very strong, I forgot the correct term, but it's like a memory effect, that it retains the dynamic nuclear orientation better than most materials, and it acts as like a capacitor for dynamic nuclear orientation. At least so that's according to the theory. Now, I've shown this last week as well, but I was kind of curious about the ARV, the Alien Reproduction Vehicle that Mark McCandless talked about. So if you notice over here, there's a aluminum flywheel in the center of a large electromagnetic coil, and flywheel means that it's spinning. And one of the things Frederick Alzofon said, and I also heard this from Richard Eskridge, that it may be possible to create dynamic nuclear orientation without microwaves just by spinning the disk in a laminar magnetic field. This is an experiment that is extremely cheap to do. You can literally do it with just a broken hard drive and a coil. You just spin the hard drive disk, which is also made out of aluminum, with a iron layer, because it needs a little bit of iron on it, and you just put that inside of a laminar magnetic field, which is a coil around it, and it should lose weight, and according to this theory. What's going on in the base is, in my current theory for that, is that it has something to do with the Podkletnov impulse experiment, that they're doing some sort of powerful impulse currents on these parallel plate capacitors, and we're going to try that as well. Let me take you over to that section of the lab. Here's our vacuum chamber, and I just zoom out. We got a lot of stuff over here. There's materials for making parallel plate capacitors, different size copper, and we also have silver, and we have a smelting furnace, so we can make all different kind of materials. This is an oscilloscope that might come useful if we want to isolate stuff, because this one works off of a battery. That's a really old school one. We got these 45,000 volt high voltage capacitors for impulse experiment. There's a 35,000 volt one. Okay, what else do we have here? Oh, this is the spy cam. You can kind of see what's going to go on over there. So the next thing we wanted to do with the Alzafon experiment is try it in high power. The low power test hasn't yielded results, but I mean, it has yielded lots of results, but I don't think any of those are really positive results, because we found lots of errors. And then once we removed the errors, the changes were in the noise range, and we weren't comfortable saying we actually saw anything. Also, the sample itself has not heated up, as David Alzofon said it did when they replicated their experiment in '94 with an 80% weight loss. So I think we're not doing something right with the waveguide shape, because we just had a waveguide coming out directly onto the sample and going out into air. So if we can get like a waveguide chamber that's tuned to the frequency, and get all the standing wave, the SWR correct, and tune it perfectly, then we may be able to, even with 20 watts, get this effect correct. But we also have the possibility of going to a much higher power setup, and this is thanks to Jeremy Riss. He was Googling on. He kept on checking on Craigslist for labs that were going out of business, and he found one locally, and he went to check it out, and he sent me some pictures. Hey, do you want anything here? And he sent me a picture of this, and it's a 5,000 volt half amp power supply, which is like, I don't even know where I would buy something like this. and he told them what he was using it for. They gave it to him for $50. So, you know, it just goes to show that you don't really need money to do this. You need more passion than you need money. $50.
Mark, if I could jump in real quick, and I should apologize for interrupting. Aiden Schaefer had a bunch of thoughts in chat. I'm not sure if you would want to answer those. They weren't questions so much as just general thoughts. He was talking about plasma sheaths and stuff along those lines.
No, not right now. Let me finish this.
Oh, shit.
Can you hear me? Okay, good. Yeah, so he picked up this power supply, and I was like, oh, that's the perfect voltage range for a klystron, which is something that I was excited to try. So we picked up a klystron from the Antigravity Research hardware store, otherwise known as eBay. And this is capable of putting out 3,500 kilowatts of power. And it's supposed to use 8,000 volts at 1 amp in order to create, which means it has a very low efficiency rating. But we're gonna put in the 5,000 at half an amp and see what that does. Hopefully, it'll be at least 1,000 watts of power, which should do the trick. From the same lab, he also got a whole bunch of these waveguides. And there was no klystron at that lab. That piece we picked up off of the eBay. And these waveguides are actually very interesting because they've been tuned to a very specific frequency, or 6.286 gigahertz. And there's a ton of tuning that went into it. All these little sticks are to tune the microwave output, and this is something that's pretty difficult to build. They weren't very clear as to what it was for, but this would allow us to put out a very accurate signal at a specific frequency, and just twiddle the knob on the electromagnet and work with that. And over here we got this is for measuring SWR, or standing wave, to see how much forward and return power you have. And this is key to figuring out when the chamber is tuned. And we got some parts that are going to be coming in the mail to work with that. This is one of the waveguides we built. I actually designed this on a 3D printer, printed it out, covered it with a little bit of aluminum. Let's see if we get a good angle on that. And we stuck the sample right inside there, right at the entrance. And it didn't warm up so much, so pretty sure it wasn't working that well. There's an isolator. That's basically a one-way valve for microwaves, just to protect the traveling wave tube. And this big device over here is this is an attenuator, but we're really just using it as a waveguide because that isolator cannot be put anywhere near a magnet. So we have the electromagnet over here. This is made out of aluminum with stainless steel bolts, so it's not going to transfer any of the magnetic flux lines to the isolator and screw that up. And we also have an isolator for the C band. This is an X band. This is X band. The C band one is over here, which is a lot larger. The lower the frequency, the bigger the equipment gets. This is also the C-band isolator. We got a double isolator because that's what they were selling. In terms of protection, we got this face shield, and also got this silver covered nylon cloth, but we're hoping that the Faraday cage will do the trick for that. Another experiment that we're going to try is, of course, the Podkletnov impulse experiment that everyone's so excited about. And Jeremiah, look at this. Look what came in the mail. We're actually
let's take a look. Give me a close up on that. Actually, let me see. Tim, are you still around? Can we get him full screen?
Yeah. Well, in gallery view, anybody can pin the video too, so that's another option.
Yeah, here I'll pin his video.
Thank you.
That's as good as it gets, I think.
Okay. Yeah. So these are the capacitors.
Those are beautiful.
They're 30,000 volts each. So that's a total of. Let me see how many of them. Yeah, there's 8 of them. So that's 240,000 volts right here on this. Right here on this bar, and there's 10 of them. So we have. Well, there's one capacitor missing. So we have about 79 capacitors, I guess. This is enough to make a 2.5 million volt Marx generator. Jeremiah's more keen of dropping the voltage a bit and paralleling them up.
We took the Podkletnov data. He has all those papers that talked about what kind of voltage and currents that he's using, and I've read a lot of alternative theories on what he's presenting there. And I believe that it has a lot to do with the actual quantity of electrons leaving the superconducting emitter and traveling towards the target electrode. And so we're going to opt in towards more of the energy levels that he was using at the kinds of potentials that he was using. And the primary reason is Podkletnov had operated up to 5 megavolts in his final experiments, but he also had a huge superconductor. And he mentioned specifically in an interview with Tim Ventura that the superconductor must be fairly wide in order to operate correctly. What Mark is showing you there on the screen, we're looking at some 10 millimeter spherical terminals that will act as our movable discharge electrodes for the Marx generator. And we have quite a few of these, so we can actually configure this Marx generator in the megavolt range, or ideally we can parallel sets of capacitors in 3s or 4s and get about 750 kV with a decent amount of joules output. But yeah, we think it's actually a electron drift effect, and so we're going to try to replicate Podkletnov by scaling down with both the voltage and the size of the superconductor, so we can get that fairly linear distribution of charge. We want that beam effect where you don't have a large amount of spreading in the actual forward moving electron emission that comes from the superconductor as a plasma to hit the target electrode.
Right. And that's another experiment I wanted to try, is using more joules of energy for the impulse, but at a lower voltage. And I'll show you that experiment in a second. Over here, we have the superconductor setup. That's our Dewar. And this is a little spill device, just for like squirting it up a little bit. Of course, we got to get our warning stickers. Tweezers, and here are the discs. They are a little bit over 1 inch, and they're fairly thick. They're about let me see, they're about 1 centimeter thick. So these are the superconductors we managed to get. We got them from,
well, now since you have 4 of them, and if I remember right, you were looking at putting an insulator between them. Have you considered? I don't know how you construct this, but have you considered stacking them, right? Like making a sandwich with all 4? I don't know if that would do anything or not, but
I don't know. I mean,
Ron Keaton knows this already because he worked with Podkletnov, and there is a layered or a stacking. I think that's what you're asking about, Tim, right? The layered superconductors. Yeah,
I was just wondering. I mean, I like you had just mentioned, right? You have a bunch of different parameters that you can change in this. I think it would be interesting. You had talked about being able to discharge them in series or discharge them in parallel or split them up, right? And discharge in multiple parallels, and that way you can balance your current against your voltage. Same thing with this. You could try making a bilayer, right, with 2, or you could try making a tri-layer or even a quad layer, I
do believe that Podkletnov actually used in his bilayer assembly 2 different types of materials, not necessarily the same superconductor simply stacked on each other.
No, and that was what I was thinking. But you could put, for instance, you could put some kind of an insulator between them, right? And so what I was wondering was you could basically make a stack of 4 of those with a sandwich of insulator between them, almost like, I was gonna say almost like Hector is doing with the gravity capacitor.
Yeah, we would need an insulator that would actually break down. It would break down in its volumetric quantity. It wouldn't break down around the edges because it's a very good insulator in a vacuum. What's going to happen is when the electric charge enters the first superconductor, it'll leap around the outside and enter the second superconductor. And this isn't, I believe, what Podkletnov was observing, where these 2 superconductors were bound, or these 2 layers were bound something that would allow electrons to actually transmit through it. But there was sort of a boundary layer condition. And I think this is, if I'm understanding it correctly, what happened, that layer would help hold back the electric charge for a period of time. And so instead of the electrons slowly seeping out of the surface of the superconductor in the vacuum and heading towards the target electrode one at a time, what they would do is the barrier between the superconductor and the interface plate would eventually break down in a way that would cause a cascade effect, and you would have all of the electrons that were stored up there suddenly move at once, and so you would get a wave front. And he actually describes being able to visibly see this as you would have a column, almost like it had a flat face on it, and it would move very quickly from the face of the superconductor towards the target electrode, and slightly change its geometry to curve into towards the target electrode, which was usually just slightly smaller in diameter.
He was talking about a blue. Didn't he say there was a blue glow discharge there?
Yeah, it's a plasma discharge inside the vacuum chamber between the superconductor and the target. But you have a beam that shows up, and instead of just having an electrical arc like a lightning bolt, or instead of just having a plasma like you would have inside of a plasma globe that you put your fingers on, Spencer's gifts kind of thing, what actually happened is you had a column of plasma that was emitting light that would move from the surface of the superconductor almost uniform, like a flat plate, as if it was a physical object, and this column would extend from the surface of the superconductor and it would hit the target electrode all at once.
I was just wondering for a second, it popped into my head. I mean, it probably was a plasma. I thought, what if that was like Cherenkov radiation?
Well, it was in a vacuum chamber with virtually no atmosphere, so
yes, it'd be plasma.
I imagine it would be.
Okay, so getting back to that, if you want to try a second type of superconductor, I have this type, but it's not this. It's a Bi2223 bar. I'm not really sure what kind of superconductor that is, but it's definitely different material than the YCBOs we have. And these are actually, they have little bits of silver on them, so you can attach electrodes pretty easily. Jeremiah had a cool idea. We're going to get some gallium and just melt it at room temperature, put that as a way to attach it to the to an attached electrode to the superconductors. And of course, if we're playing with superconductors, we got to do the Meissner effect and make a Meissner track. So we got a whole bunch of magnets for that. That's just cool eye candy. What other experiments are we trying? Oh, so we talked about the high current option. So we have all of these capacitors over here. I was debating whether to go crazy and get like the 22,000 joule capacitors that they sell on eBay. Those things need to come by freight. And Jeremiah kind of talked me out of it, but still not sure whether I want to do that or not. But for the impulse part for that experiment, we want super high speed, which is why I got this this Thyratron. This Thyratron is actually from the decommissioned linear accelerator at Berkeley Labs, and I believe this piece actually helped discover two elements, 97, 98, americium and berkelium, or Berkeley, America. Oh no, californium and berkelium, yeah. And right now we're going to try to use it for another experiment, and may possibly use it for two great scientific discoveries, which will be kind of cool. As Banduric was mentioning, yeah, everything needs to be separated, especially with high voltage, which is why we have this massive battery, which I just picked up from Hobby King. Reason why I need such a massive battery is because this thing sucks a lot of energy. It's like 500 watts or something like that. So 6.3 volts. No, it's like 150 watts just to power the coil in there, the heating element. This is capable of pulsing 186 megawatts of power. So if you have enough power available, this can pulse it within like 4 or 5 nanoseconds. Extremely fast impulse speeds. Now, to control all that, we already have the circuit built, which you see right over here. Basically, all of the electricity is coming in from the battery via this wire. I'm going to have to change the connector. And this is a high voltage, DC to DC high voltage converter. And that is for the filament, or the grid voltage. It needs to be negative A negative 200 should do the trick to hold back 35, 40,000 volts. This is the this is a photo. It has like a little optocoupler over there, and we attach a fiber optic cable to that to turn this on and off, or turn its connection to the tube on and off. And I couldn't find a DC to DC converter, down to 6.3 volts that had enough current capability, so we had to double them up. This same concept of a device is actually built right over here. I've been using this for one of my earlier experiments, and this tube is only capable of putting out like 5 watts. But it's able to go up to pretty high voltages, which is why everything's covered in Kapton. I've used this for a couple of experiments. This was way back in the day before I had all the proper test equipment to, to weigh the samples, but I did see very anomalous results. I'm not going to say that anything actually happened because the scale was not properly grounded. So again, we're dealing with piezoelectric effects, getting affected by the strong EMPs that are coming out of, my setup. So we got to be careful about that as well. Another tube that we got, Jeremiah, this is basically a diode tube. And I think this was for the Banduric experiment, right, Jeremiah?
That's a rectifier tube there?
That's the rectifier tube, yeah.
Oh, sweet. Okay, awesome. Well, we have quite a bit of potential then. Yeah, we can run a lot higher than he did in his experiment in terms of potentials. And darn, I did forget to ask Richard a question. I wanted to ask him about insulation on the surface of the dot. Oh, hey, Richard, I wanted to ask you about the insulation on the surface of the dot product plate and the cross product plate. If we insulated them to a very high degree with a fairly thin, very high dielectric withstand dielectric, and ran them very close to each other, would we not be able to get a significantly stronger force at a higher potential as a result? Or would that insulation affect the outcome?
No, I think you would get higher force as long as you make sure there wasn't a charge that accumulated on the insulation itself. That's the only thing I might worry about. But
Ooh, yeah, with ions, it's going to definitely accumulate on the surface. I have a feeling it'll pull it right out of the air. So I guess you almost need to run it in a vacuum, hey?
Yeah, maybe, or in some kind of matrix of some kind. So that diode you guys got, is that one you're thinking of using? That's a pretty big diode.
Yeah, it's it's definitely pretty large. We took a look at several other options that we could run off battery packs, and we really want to run that isolated system off some lithium ions just to fully test it. But we would like to try significantly higher voltage than what you were operating at, just using the same principles. So we can, with our poor scaling equipment, because we obviously don't have the absolute nicest equipment in the world, but we have some decent stuff to work with. We wanted to make sure that we were beyond our noise floor, so we probably need to operate at a higher potential than what you were doing.
Okay, yeah, but there's all the difficulties with having high voltage around that makes it a real pain in the butt.
Sure does. Lots of shielding, lots of isolation, right? But one of the ways we found that works best is to stick it on a platform that's suspended by a yarn or string or fishing line at a significant distance away from the fully shielded EMI suppressed scale.
Yeah, that sounds like it would work.
Okay, so moving forward, we're going to use this to impulse it, but what are we going to impulse into? One idea was to go into the gravitator, which is based off T. Townsend Brown's, patent about how the dielectric material or the glass in between the lead plates, whatever, would lose weight, and it created a pulse or something like that. We've replicated this experiment a couple of times, and we just found false positive after false positive until we finally managed to get rid of all of the variables, and then we got no result. But, and this is kind of very important, we had a guy in Vietnam, Mr. Nam Tran, and he kept on trying, and he even went to the effort of sending over his capacitor, parallel plate capacitor design that he built, and he wrote on it, the amount of weight loss and the voltage. We tried it and we didn't see any weight loss, but then we started looking at his power supply and we realized something very interesting. And Jeremiah, you can take this away. was something very interesting that we discovered about his power supply that brought about the effect.
Yeah, gladly. So NAM had a very interesting configuration. He sort of did his own thing, and when he did, he designed a voltage multiplier with an odd number of stages, giving him an AC output at the high potential point. So a voltage multiplier normally just rectifies the output of the transformer and multiplies it. So you get a DC output, a fairly steady one that's rectified by, or that's smoothed out by capacitors. But he actually put his output on the AC side directly coupled to the transformer. So in addition to the 50 kilovolts that he also had some potentially 7,000 volts AC at about 22 kilohertz riding on top of that signal. And even though his system was not technically isolated, it did have a ground connection. The fact that there was a changing rate flow of voltage in that system could have caused the results that he was observing. Now, he's tested not only the device that you see in front of you in the center of the screen there, but he has many, many variations. I couldn't even count how many now that he's tested. And he usually receives results as an artifact of having this AC strange supply that's not quite isolated, but does have this component that's changing with time. So we're working on developing a version of that which is isolated and also develops that change rate component of time so that we can really maximize the effect and test it independently of other variables.
Yeah, and I got all the components that he told me he used. They're right over here. Got the diodes in here. We got the flyback.
Like good scientists, we're going to exactly duplicate precisely what he built, up to and including the highly leaky connection points between each individual component. He didn't solder his wires. He actually left the ends of the terminal leads for the capacitors and diodes exposed to the air, which means each of those stages would discharge. And so considering he already had an AC on his system, so that AC didn't just simply build up and reach DC potential where it didn't come back down, because it is diode isolated, he was leaking ions the entire time around his power supply, which means that he would get a somewhat sinusoidal, or probably more like a saw wave tooth type of waveform on the output riding his 50 kV DC. So we're going to replicate that exactly as he did and try to duplicate his results.
And also, we're going to be able to actually see the high voltage output, because here is our high voltage rack. Okay, over here we have, this is a 125,000 volt DC 5 milliamp power supply from Gamma. Below it is also from Gamma, is a 100,000 volt voltage divider, 10,001. So we're actually able to hook up, and it's basically an oscilloscope probe. We're able to hook up an oscilloscope and see a 100,000 volt signal and graph it on a on a scope, which is pretty freaking cool. Up here on top, I picked this up off of eBay. It was like $300. Maxwell Laboratories. This is a 45,000 volt power supply, and it actually matches our capacitors over there. These 45,000 volt capacitors, and this is what we're going to be using to power up all our Mark's generators and all that stuff. This puts out 8 kilowatts, which is freaking amazing that it can do that. So 45,000 volts, 8 kilowatt power supply. This is a 125,000 volt, 600 watt power supply. And there's a voltage divider over there, which is basically just an oscilloscope probe. And it's all on this movable rack. We also have a whole bunch of motors over here. We like to pick through the garbage for stuff. And you can find a lot of equipment in the garbage. And that's something that Jeremiah is teaching me how to do. Like, for example, this material over here comes from the back of a flat screen TV. And Jeremiah has a lot of experience with high voltages, and he found that this material actually works as an amazing insulator. It's like, I don't know, it's extremely thin, and it's able to withstand like 50,000 volts. So the dielectric strength on this material is amazing. If you've ever seen a broken LCD TV being thrown out, you can rip out the back of it and grab that sheet and do your high voltage experiments with it. Works better than Teflon. I'm not really sure what that material is, but it works great.
It's a type of plastic that actually has a grain to it. The way that it's extruded causes it to have particularly unique and useful high voltage properties. And yeah, at 50,000 volts for a material that's roughly about 3/4 of a millimeter thick, that's a pretty decent voltage withstand ratio. And if you stack those layers up, I mean, what we kind of did, which was fun, is we took some sheets 10 inches by 10 inches. We cut them out of this material from several different LCD TVs that we found in the dumpster. And we sliced them up. We charged each of them up with a device that I just call the electric magic wand. It's a 130,000 volt handheld voltage multiplier that runs off a switch mode power supply at about 400 kilohertz and off 2 lithium ion batteries. So we charge those up, and what you can do is toss the sheets on top of each other after you deposit some ions on the top, and what you'll end up with is a few 100,000 volt discharge that will leap around the outside. But what you show them your stuff, Mark, and then I'll go ahead and show some garbage gadgets that I got here.
Oh yeah, so Jeremiah is the king of dumpster diving anti-gravity research. So I'll just give you guys a little pro tip over here. This is a wire that you get from hvstuff.com. They claim it's able to withstand 150,000 volts, which is complete and utter bullshit. I actually broke equipment. My 125,000 volt power supply broke down at 70,000 volts and fried some internal components. So we had to go and fix that. If you want high voltage wire, me and Jeremiah found this independently. We found that this little red wire over here, and it has this funny cross section on it, is actually able to withstand amazing voltages. I got some more of it on eBay over here. This stuff is really, really good.
It has a coating that's similar to an ABS plastic, but with more flexibility, and it has a high-density polyethylene internal insulator along with a small cross-sectional conductor, which is composed of a multi-stranded wire to not create stretches. So that particular wire is fairly small. It's rigid, which is unfortunate because it's hard to work with because of that, but you can put stupid amounts of voltage through that stuff.
Right. And these are the things that you only learn from being in the field and actually working with these.
Yeah, that other one looked like it had kind of a soft. The one that you said broke down, that looked like it was kind of a softer. You know what? Those degrade over time from the air. I bet that's probably what's happening to it.
No, it was leaky from the start. Yeah, you could feel it. You could hear it hissing all over the place. I really think the Chinese need to up their game with their quality control shit. And that's really what it comes down to. In here you can also see some of my earliest experiments with high voltage transformers you buy on eBay, and there's just a bunch of Teflon and PVC and all that stuff. This is basically the box of dielectrics that we're going to use for the high voltage experiments. One thing that I really like to do is to up the dielectric strength properties of any wire is to use a Teflon tube within a Teflon tube within a Teflon tube. And this is really the best way to go, because then you can, depending on the voltage that you need, you're able to make a custom thick, covered wire, and you just use this red stuff in the center. And this stuff is difficult to find. If anyone out there wants to replicate these experiments, you can hit us up, and we'll give you the link to where we purchased it last. Okay, so what is next? Oh, so was it Banduric's experiment that's spinning?
Oh yeah, it is. The two rotating discs.
Rotating discs, exactly. So this is an 800 watt, or it's nearly 1 horsepower RC motor, and I'll believe it when I see it, because this thing is tiny. If this could put out 1 horsepower, I'll be shocked.
It's possible.
You really think so? Look how small that is.
Well, think about the magnetic field strength, the coupling coefficient between the core and the stator. And I know the shaft is ridiculous, but it spins at such a high RPM if you calculate your torque ratios. It is possible for it to put out a peak of over 1 horsepower. It wouldn't do that continuously. It would catch fire, but it can certainly generate that peak. And if you're doing, some maneuvers with your quadcopter or your helicopter, you can certainly expect it to be able to perform for a short burst at that kind of power and power input.
I don't know, Richard. What do you think? Do you think this will do the trick?
I've had the biggest problem with using motors that are controlled electronically with a motor controller, because when you have high voltage floating around there, it always gets in the wrong place. I've had better luck using the very old motors that don't need a controller.
So Richard, what I have here is a 28,000 RPM DVD-ROM drive brush motor, and it's kind of hard to find the brush motors, and to find a couple of high voltage or a couple of high speed brush motors. They operate real nicely at 12,000 RPMs with some better lubrication on the bushings. I stripped off the surface of a CD, and these are conductive. They're not incredibly conductive, but I took all the coating off, and so I end up with something like maybe 60 ohms across the surface. Do you think this would work as my cross product disc?
Yeah, I think it would. It would. That's what I did. Is we would just we would deposit a material on an acrylic disc like that. And so, that's chrome on there for sure. So that'll probably work.
I could be way off base, but if I could chip in, do you think that there might be a way to etch the actual material on the CD-ROM to make it perform similarly to the silver epoxy? Because if there was a way to do that, right, I don't know how you do it, but if there was a way to actually modify the material, then it would be easy as heck to generate test platters.
The issue is for the dot product disk, in order to have it operate and respond relativistically, all the charges that are independent of each other have to be isolated. So if you had a solid material that electrons could flow from one material or one area to the other, they'll transition and they'll move through it. If they're not isolated, you're not going to get that force, that upwards non-reaction force that doesn't equal zero unless those charges are isolated. So what he was talking about last time too, on the last APEC meeting, was you saturate the epoxy and microbead system so that when you pass a high voltage through the microbeads and epoxy, they're close enough where you get charging of the microbeads. But after that, if there's a small voltage change, a relativistic voltage change, for example, because of the RPMs of the cross product disk that's spinning, your voltages that are developed in the dot product disk will not be able to escape. And as a result, they'll experience a force that's not equal and opposite. If I understand that correctly, Richard?
Yeah, and then use a high voltage power supply just to make sure that the charge doesn't leak out of it, right? That's the only reason you keep a power supply on it, because once you get it all charged up, it doesn't take that much current anymore.
Right,
Richard,
Richard,
so you're saying that this ESC, the electric controller for the motor, is going to have trouble at the 20,000 volts. How many volts are we talking about, actually?
Well, no, it doesn't have power. The problem is it's so hard to isolate 20,000 volts from just sparking somewhere the wrong place. It doesn't need to, because those FETs and those things, if they even get a hit with a small spark of 20,000 volts, they're actually going to short out, and then everything's going to go up in smoke. So that's why I say it's better to use an old motor with brushes and, stay away from the electronically controlled motors with a motor controller. Because you don't really need a lot of force on it. You're going to spin a disc. These discs are relatively light, so you don't need to have a horsepower or something. A very small motor will work fairly well.
Well, okay.
And by the way, Mark, I'm sure we can make that work at 20 kV. We can easily isolate that and Faraday cage that system with the battery. And if we wanted to float that entire thing, we could float it at 20 kV without it really being affected. I mean, the RC receiver is not going to have a problem. Just the fact that it's floating 20 kV above ground or something. It won't.
Okay, yeah, that's the only reason I'm concerned is, if you guys can do that, they should be just fine.
So guys, it's Tim. Let me jump in real quick. We are coming up on the top of the hour. So I just want to see what does our timeline look like? What's our schedule look like?
Let me just finish. There's a couple more things that we didn't go over yet. Okay. So we also have these servos. I got a couple of them, and that is for the gyroscope experiment that we talked about last week, or I think it was actually 2 weeks ago when we were last live, where we have the gyroscope spinning up and down and sort of swimming through the ether, or however that works. So we're going to try that with 4 gyroscopes, and we'll put them out of sync so that there's always one moving forward. So you're going to have like 2-phase electricity or something like that, because he was mentioning that there's a problem that it's AC versus DC. So let's try to fix that problem with another set of gyroscopes and see if it works on a pendulum system. That's another experiment they wanted to try. Also about the high voltage impulse experiment. So what are we impulsing it into? We could impulse it into the parallel plate capacitor, but there is no real energy storage here. There's just the plates themselves. So in order to spice it up, we got these high K materials. I got barium titanate, which is, it's been the go-to for capacitor makers for a while. Then there's this new material called calcium copper titanate. And according to the Chinese, it has a dielectric constant of 200,000, which would make it probably one of the highest K value capacitor materials I have ever heard of. So if that is true, this will make some really awesome capacitor plates. We got a press coming in the mail that Jeremiah's gonna help me hook up, and that is going to, press all these materials into a nice cake, and we'll be able to make really high power, dense parallel plate capacitors for these experiments. Let me see what else we have going on in the lab over here. For the Marx generator, Jeremiah thinks that it's going to put out a sound impulse on the order of 180 decibels. So we got earmuffs protection. Also, another thing that's going to be really cool, which you guys are all going to see, is our studio production. We're actually hired a professional cameraman and editor. And here's some of our, part of our camera setup. This is going to be, 4K imaging for the lab. And for the Faraday cage, we got a bunch of these GoPros, and we are going to put them inside their own little Faraday cage. And to protect the lens, we got this silver mesh, fine wire cover that's going to go over that. And then on top of that, we have a leaded glass that's going to cover it as well. And the rest of it is just going to be covered with aluminum in order to protect the camera from the big EMPs. And let me see if there's anything else. Oh, this is a sample of one of the gyroscopes we're going to use for that experiment. This is a pretty old one. The bearings are starting to go, but I ordered a whole bunch more, and they are on their way. Oh, and this is one more device that just came in the mail. I just powered it up. This is a LaCroix 16 gigacycle per second oscilloscope. Still works. It's pretty old. And this thing brand new probably costs on the order of like a small house when these things were new. But as you can see, it's not pretty new at all. It actually has a floppy drive. That's where it stores the data, I guess. So I actually had to go onto Amazon and find a floppy to USB converter along with a couple of floppy disks in order to get the data off of this oscilloscope. We're going to use this for the high impulse experiments. We're probably going to hook it up to the voltage divider over there in order to get exact times of the impulses. How many nanoseconds it took to fully charge the capacitor, so we get an idea of how many joules per second we're dealing with. And that's about it for the lab right now. And we have more equipment coming in later in the week. And Jeremiah is going to be here on Monday. He's be flying in from Milwaukee, bringing some of his equipment as well. And we're going to be doing tons of experiments. Sorry for all the mess, but it's going to look a lot better once we have stuff set up. I plan on doing a similar setup like this with the camera where you can see us from multiple angles. We'll have one laptop showing you the live data, and then we could have cameras showing you, the lab in action, as we're setting up an experiment, and have open discussion as well. So you guys take it away now.
Okay, well, so let me see. Aiden had, again, I'm going back up here. If he is still, you know what he might have. Aiden, if you're still here, he might be hiding.
No, I'm here. Can you hear me?
Yeah.
Test.
Perfect.
Hi. So in 2010, I had a major eyewitness, or my first UFO Encounter, and it was two crewed vehicles had come down, and they were doing a low, slow flyover of Holy Cross Hospital, the local hospital here in Taos. The vehicles had released a group of spheres, and over the years, I've come to learn that those are their scout platforms. And over the next couple of years, I lived down in Albuquerque around Sandia Labs and started watching the sky. So I've seen these crewed vehicles release small glowing spheres a couple times. But so in 2010 and then again in 2012, these crewed vehicles released the spheres and they cloaked. They in 2010, it was a horizontal. They were about 1 kilometer away, and they just shimmered and you stopped seeing them. The sighting in 2012 was down in El Paso, and the crewed vehicle was up at altitude, and it released another one of these small spheres. And the best way I can describe it is like take a ball, throw it, and imagine that it's spinning, and then as it spins, it spins into nothing. So the propulsion field does spin around the vehicle. I think they generate an asymmetrical field topology on the aero shell of the vehicle in order to get a directional thrust if they're cruising around the planet. So yeah, I don't know. I mean, I've got about 10 years of observations now, and then David Mathis, who was here earlier, has mentored me for a bit. But so yeah, I know that the propulsion field spins around these vehicles, and it's asymmetry fields allow it to move in different directions.
I might pick up on that a little bit. So dynamic nuclear orientation can also explain the invisibility factor that we see with some flying saucers or intergalactic extraterrestrial spacecraft. Basically, when you interact with matter, you're not interacting with the core of the atom. The core of the atom gives its inertial mass, but when you're touching your desk right now, you're actually touching the electron field around it. So the electrons are what we really interact with, for touching things, and then the core is what gives it its inertial mass. The electrons are what the light, the photons hit and bounce back off of. So that all happens because of the randomness of the electron field, which is why quantum mechanics is all about probability, because you can't, graph randomness. But if you create coherent matter with dynamic nuclear orientation, all of the electrons are all spinning on one plane, and from certain angles, the light will travel right through it because it won't interact with those electrons the way they normally do. So there is a switch on these craft to turn off, make them invisible from certain angles. It won't work. It's not 100% invisible, because you can see it from the side, and I don't think it's going to work 100%. There have been many intergalactic extraterrestrial spacecraft that have been seen to create like a shimmering effect as they fly overhead. Like the Phoenix lights is a great example of that.
John Hodgson has seen that effect too a few times. He's seen things become kind of translucent, transparent, invisible, various combinations.
It's like a means not fully transparent, but a distortion, something like a distortion in the sky.
Oh, Kishla, you said you've seen a couple of them in India?
Yes.
Is the distortion around the edges, or is it like in the center?
Like in a few sightings, I have experienced that the whole shape means if it was a circular distortion, like an oval shaped, and the UFO was not visible, but the distortion was moving, like it was in a cloak. And in another sighting, it was very clear. I saw it at the zenith, at the top point of the sky at midnight, that it was a triangular shaped, and it had three very faint sort of propulsion, any mechanics or something which were emitting very faint lights. I saw it and it traveled very slowly and stealthily.
Oh, that's very interesting. Does anyone else have an experience seeing a?
Actually, I had many, means at least 7 to 8 sightings, but cannot clear that these were UFOs or not. Once I had saw a very fast dot, which traveled from zenith to the horizon in just 4 to 5 seconds, and my mother also saw that. That's very interesting, and also a dot, like a dot. That dot came and suddenly like a door made of light, nothing but light, and it came and like teleported into it, just boom, vanished.
I just want to make one point. We're trying to stay away from the word UFO, especially UAP, because a UFO is a bird. If you don't know what type of bird it is a UFO to you. And so is an airplane if you don't know what model it is. So yeah, UFO is sort of like a meaningless word that has destroyed the credibility of this field. So let's go with flying saucer, flying triangle, or interstellar spacecraft for that.